Welcome everyone, and hopefully you have had a wonderful start to the new year. My name is Valtteri, and I'm a developer at Xiphera, and I am your host today for today's webinar. If you have already found our webinar series and are a returning viewer, you probably know our company already pretty well. But let me introduce us real quick for those who are not so familiar with us just yet. So Xiphera is a Finnish company founded in 2017. We design hardware-based security solutions using standardized cryptographic algorithms, and we offer implementations of those algorithms as intellectual property cores or IP cores. Our product offering includes cryptographic algorithms, protocols, and furthermore, we design our IP cores mainly for field programmable gate arrays or FPGAs, but our offering can also be integrated into ASICs and SoC platforms. You can always check out Xiphera.com for more information to see for yourself about our offering after the webinar. And if the upcoming presentation raises any questions, small or large, please submit them to the Q&A box found at the bottom of your screen close to the chat icon. We will have a Q&A, questions and answers session after this presentation. And for your information, this webinar is also being recorded and it can be found from our website a few days after this webinar. And now we can move to our actual agenda. May I introduce you to the star of this event, Dr. Matti Tommiska. Matti is the managing director and co-founder of Xiphera, and he has his master's as well as doctoral degrees in electrical engineering. And since his extensive academic career, Matti spent 13 years in both technical and sales roles in leading semiconductor companies, prior co-founding Xiphera in 2017. But for now, I will let Matti talk for himself. Go ahead, Matti.
Thank you, Valtteri, for the introduction, and let me also welcome you to participate in this Xiphera webinar. I will talk about randomness and its importance, and after I have finished, Valtteri will take care of the Q&A session. So today's agenda is as follows. First, we will address the topic and importance of randomness and look at a couple of use cases for it, including, obviously, and very importantly, cryptography. There are a number of important standards related to randomness, and next we will review a few of them, as knowing these standards is vital, especially if you plan to design and implement a random number generator yourself. So speaking of random number generators specifically, we will conclude the presentation part of this webinar by reviewing the internal structure of random number generator, and also spend a couple of minutes to discuss a very important topic, namely the testing of random number generators. Now, randomness as a topic has fascinated mathematicians and computer scientists for a long time. And on this slide, I have collected 3 quotes from 3 famous mathematicians. Now, these quotes all have a common theme, but let's first quickly read through them all. Now, Robert Cavill wrote that the generation of random numbers is too important to be left to chance. Random numbers should not be generated with a method chosen at random. This is a quote by famous mathematician and also computer scientist Donald Knuth. The last quote is, anyone who considers arithmetical methods of producing random numbers is of course in a state of sin. Now, this memorable quote belongs to I would call him a universal genius, John von Neumann. And the common theme in all these quotes is that generating randomness, that is random numbers, or more specifically in digital world, random bits, is very important. And special care must be paid to design a reliable and well-founded method to generate randomness. Now, we can also approach the topic of randomness through a hopefully illuminating example question, which is presented on this slide. Now, as you can see, there are 4 bit strings, that is strings of ones and zeros on the right side of the slide, and each one of these bit strings is of the same length, namely 16 bits long. Now, importantly, we observe these bit strings in isolation. That is to say that we do not know anything about the bits that may have appeared before them, and likewise, we don't know anything about the bits that may appear after the 16-bit long bit strings. All we are able to observe are these 4 16 bits long strings. But we do know that the source producing these bit strings outputs ones and zeros with equal probability. And the questions are, now, which one of these 4 bit strings is more random than the others? And which ones are less random than the others? And I will let you think about this for a couple of seconds. Now, you probably came to the right answer by now, and the answers are that all of these bit strings are equally random. And remember, we observed these bit strings in isolation and did not know anything about the preceding or subsequent bits, and we only knew that the source outputs zeros and ones with equal probability. And with basic mathematics, the probability of all these bit strings is equal, namely 1 over 2 to the power of 16. They are all equally probable outputs from the source. Now, let's talk about where randomness is used in concrete terms. And very importantly, the security of the internet is fundamentally based on the ability to generate random numbers quickly and reliably. As an example, every time when you connect to a secure website, for example, online banking, random numbers are being generated and used to construct the secret keys which enable secure browsing. This all happens in the background without you not necessarily knowing about that. But indeed, cryptography, which is obviously the main interest for Xiphera and also for this webinar, is probably the main user or customer, if you like to call it that way, of random numbers. As random numbers, random digits, random bits are used for secret keys, so-called initializers of vectors, and also other use cases in cryptography. Additionally, and interestingly, random numbers are also used in a number of other fields, including but not limited to, for example, statistical simulation of complex systems, and also importantly and maybe somewhat entertainingly in games. Now, for example, who would like to play a 100% identical version of your favorite game every time you start it? That's why randomness is used also in gaming. Central to the topic of randomness is the concept of entropy. And entropy in information theory can be loosely defined as the unpredictability or perhaps unguessability of a symbol or variable. And the symbol is most often in a bit 1 or 0, but without loss of generality, symbol can take on any possible value from a certain set of allowed values, also bit strings. There are different entropy definitions, but probably the most well-known mathematical definition belongs to Claude Shannon, who in 1948 formulated the entropy formula as is shown on this slide. And I'm not going to go through all the mathematical details in the formula, but to simplify this in layperson's terms, if we limit ourselves to the digital world of ones and zeros, the closer the Shannon entropy is to 1, the more random or unpredictable the single bit output of a source, also known as an entropy source, is. And more about the entropy sources soon. Importantly, the concept of entropy in randomness and cryptography and information theory is different from the entropy concept in thermodynamics, which may perhaps be more familiar to you, but it's different. Now, this slide has 4 examples of entropy sources. This is not an exhaustive list, but hopefully a representative list of entropy sources which are actually in use. Now, first, let's look at the well-known website random.org. And I encourage you all to visit that site. Maybe you already have done so. But that site lets the visitor generate random numbers. And the generation mechanism is based on measurements of so-called atmospheric noise. This is primarily lightning discharges in thunderstorms. While the website is obviously well-known and respected, obviously its usability for practical applications is very limited because the generation of random numbers is very slow and you have to be connected to that site. But for, I would say, isolated individual cases where you need just a handful of random numbers, you can use that service. Now, another increasingly popular category of entropy source is based on quantum mechanical phenomena. And there are a number of also commercially available so-called quantum random number generators, QRNGs, available. These are typically fast, and also the stochastical models, more about that later in this presentation, of quantum mechanical phenomena are usually well accepted. Now, when we come to the bottom row, say more traditional electronics, one option is to use so-called discrete external components as entropy sources. A well-known example is a so-called reverse biased Zener diode, where current is randomly conducted in a process known as an avalanche breakdown. Obviously, one of the disadvantages of discrete components as entropy source is the potential vulnerability to external disturbance by, for example, attackers of cryptographic systems. And importantly, one can also design an entropy source inside an integrated, say, digital semiconductor chip, like a field programmable gate array, FPGA, or an ASIC, application-specific integrated circuit. Now, this is a widely researched field, and there are a number of mechanisms that have been studied, analyzed, tested, and modeled. Examples, once again, not an exhaustive list, are using so-called carry chains in FPGAs, or to use PLL's phase lock loops in FPGAs, or to use ring oscillators, both in FPGAs and ASICs, and so on. Now, because randomness is so vital for information security, including obviously internet security, relevant standardization bodies, including obviously the US-based National Institute of Standards and Technology, or NIST, have over the years published several standards related to random number generation. The most well-known and very likely most implemented standard series is NIST SP, or Special Publication 800-90 series. This series includes 3 different standards, 90A, 90B, and 90C from the past several years. Everyone who wants to design and implement a random number generator should read all these 3 standards, as they specify how a NIST standard compliant pseudo or true, and more about these 2 versions in the next couple of slides. Random number generator should be designed and tested. The official names and also a brief summary of the contents of the NIST SP 800-90 series is therefore presented on this slide. And another important standard is also available from the German standardization body BSI, and this standard is called AIS 31. As I already mentioned on the previous slide, random number generators and also random bit generators, which obviously are a subset of random number generators, can be divided into 2 main categories, namely true random number generators and pseudo random number generators. The word pseudo originates from the Greek word pseudes, which translates to false. And while this may sound a bit harsh, the implication is that pseudo random number generators are not truly random in the real meaning of the word random. namely because a pseudorandom number generator is deterministic. In other words, it always produces an identical output sequence of numbers or bits with the same initial conditions. This is obviously not the case with a true random number generator, which is based on an unpredictable, unguessable entropy source. Now, for a pseudorandom number generator to be used in a cryptographically secure critical application, it must be periodically be reseeded. In other words, sort of resetted into a different initial condition with fresh entropy, typically from a true random number generator. Now, pseudorandom number generators have many use cases. They are typically faster. That means they generate more output bits or numbers per second than true random number generators. And the implementation of pseudorandom number generators can also be done in software. An important side note is that if you start reading the NIST standards, which were listed on the previous page, they somewhat unfortunately have their own terminology for both true and pseudorandom number generators. The NIST terms, non-deterministic or deterministic random bit generator, are listed on the right-hand side of the slide. But in this webinar, we consistently use the more common terms true and pseudorandom number generator. Now, this slide presents a structure of a real-world true random number generator. And at the top of the block diagram, you see the core of the true random number generator, which is the entropy source. This outputs so-called raw bits, a string of zeros and ones, which is supposedly random output from the entropy source. These so-called raw bits are continuously tested by so-called online health tests, and I have more about them on the next slide. So let's put that topic aside for now. And only if these raw bits pass the online health tests, they are collected to an internal buffer. And once there is internal material in the internal buffer, a certain batch of these collected health test tested bits is then sent further to the so-called entropy extractor. And we'll talk about entropy extractors also later in this presentation. And the output of the entropy extractor is then collected to the output buffer. And importantly, the customer or client or user of random numbers never actually has access in the default case to the output of the entropy source. But the offered random bits are actually the output of the output buffer. They have been health tested and also entropy extracted. Now, the testing of random numbers is obviously a very important topic. And the testing can be roughly divided into two different categories: online testing and offline testing. The online testing is basically the, I would say, the consecutive and continuous testing of the bits from the entropy source. And I already mentioned this on the previous slide. The NIST standard SP 800-90B mandates the use of two health tests or identical functionality. And these two health tests are repetition count and adaptive proportion. And a brief word about repetition count is that it basically checks for a consecutive strings of identical ones or zeros in the output of the entropy source. And if it starts basically outputting a consecutive string of tens or hundreds of ones or zeros, then basically these bits will be discarded and not be sent further to the entropy extractor. The adaptive proportion test looks for a batch of bits, 1024 bits as an example. And if the distribution of ones or zeros in this batch of bits is too skewed, meaning that the proportion of ones to zeros or zeros to ones is too, I would say, too at the extreme, too much at the extreme, also this batch of bits is then discarded. Also, startup tests are obviously always run on the entropy source every time when it's turned on or resetted. A separate and yet a very important topic is the offline testing of the entropy source output bits. And for these offline tests, typically a very large amount of data needs to be collected from the output of the entropy source. Concrete example, gigabytes of data have to be collected. And basically, these statistical test suites run through a number of tens, hundreds of statistical tests and test for the quality of the entropy source output. Now, the official standard for NIST is specified in special publication 800-22. This is currently being reviewed, and it also has been somewhat criticized in the cryptographic community for its supposedly too lax testing of the entropy source outputs. And I would say that the de facto tests, statistical tests for the output of the entropy source are ENT, GJRAND, PRACRAND, test U01, and they are recommended to be used. Now, the fact that the output of a random number generator or entropy source passes the statistical tests is a sufficient requirement for a true random number generator, but it's not sufficient on its own. They also have to be tested for the stochastic model, and the stochastic model is a requirement for the entropy source. So basically, this means that the entropy source needs to be based on a well understood physical phenomenon that has to be able to be modeled mathematically. And my favorite definition of a stochastic model comes from a German BSI, and it's listed on this slide. Now you should know that the BSI word for an entropy source is noise source, but replacing noise with entropy in this definition gives you a very good overview of what a stochastic model is. Next, we go to the entropy extractor. If you remember the block diagram a couple of slides ago, this was a step before the output of a true random number generator is available to the consumer or client. And basically, the role of the entropy extractor is to increase the entropy per bit. Now, remember, entropy is loosely defined as unpredictability. The role of the entropy extractor is to increase the entropy per bit close to its theoretical maximum 1. But however, importantly, this happens at the expense of the output rate from the entropy source. The overall entropy of a bit stream cannot be increased. Now, NIST has standardized a number of entropy extractors, also called conditioning elements in NIST terminology. And likely the most widely used is AES-CBC MAC, where the well-known advanced encryption standard is used in Xiphera blockchaining, therefore the CBC abbreviation mode to calculate a MAC. As an example, the input to the AES-CBC MAC, in other words, the input is the online health tested output of an entropy source, could, for example, be 512 bits, and the output would be half of that 256 bits long MAC. And the entropy per bit in the output is larger than the entropy per bit in the input, but the overall rate is half. Also, a number of other entropy extractors have been standardized. If you are interested in the details, please check out the NIST SP 800-90A standard. Now, we have so far focused almost exclusively on hardware-based entropy sources and hardware-based implementations of entropy sources. So perhaps it's a good time to spend a few moments also on the software side of things. This is a simplified and high-level description of the way the Linux operating system provides random numbers through system calls, such as getRandom, which is the recommended one to a software developer. Now, the operating system maintains an entropy pool of 4096 random bits, and this entropy pool is refreshed by fresh entropy or randomness from, for example, hardware-based random number generator, especially at boot time, from CPU's random number generator, if the CPU supports that, and also from random timing information from interrupts, mouse movements, keyboard strokes, and so on. And the amount of remaining entropy is also being tracked. Internally, the entropy pool sort of mixes the entropy with a construction known as a linear feedback shift register. And the abbreviation PRNG stands for cryptographically secure pseudo-random number generator. And Linux has lately started to use the stream cipher known as CHA-20 as the underlying mechanism for PRNG. Now, if you want to experiment with a real-world FPGA-based true random number generator, and importantly also test the output. Literally, you can get multiple gigabytes of random bits and test them with a set of statistical test suites, which are well listed a couple of slides ago. You can visit the link here. Like Valtteri said, the slides will be available on Xiphera's website in a couple of days, and do test runs by yourself. The Xiphera true random number generator runs on a real FPGA on AWS cloud, and everyone can test it, and its output for free of charge for 14 days with no strings attached. Now, this slide has a collection of good sources and references if you want to learn more about random number generation. The relevant standards, which were already reviewed a few slides ago, all three NIST standards and the German AIS 31 are listed here. Like I said, they are pretty much mandatory reading for everyone who wants to design and test a random number generator by himself or herself. Please also note that the standards are obviously updated every now and then, so always make sure that you have the most recent version at your desk when you start designing and implementing a true random number generator. Now, on a maybe more approachable level, I would recommend this very readable book on randomness by David Johnston. David works at Intel, and he's been very much involved with the development of the random number generator in Intel's processors. This book has a pragmatic approach, and it discusses the mathematics of randomness in a very, I would say, approachable way. Now, lastly, I also need to mention that Xiphera has a web page dedicated to random number generation, and you are obviously welcome to check it out as well. Now, I want to thank you for listening to this webinar presentation, and hopefully you found the information useful either in your work or in your studies or both. And before I hand over to Valtteri to host the Q&A session, let me invite you in advance to the next Xiphera webinar in early summer. More info will be coming soon.
Thank you, Matti. Well, who would have thought that randomness could be so crucial part of our everyday life, and so important in cryptography and our online security. And now it's time to go through your questions, which you can still post in the Q&A box next to the chat icon. So let's see. Here is a practical question. So how is a TRNG integrated into a system? For example, a Linux computer?
Yeah, that's a good question, and I also sort of go back to a couple of slides because we sort of touch on that already in this webinar. So as you can see on this slide, the TRNG would be represented by hardware random number generator, and for example, in modern FPGAs, you have families where there's both a processor and an FPGA subsystem available, and this true random number generator would, for example, be implemented on the FPGA side of these SoC devices, and basically the Linux operating system would be running its R&D subsystem on the processor side, and that would be the way to integrate the random number generator in a Linux environment, I would say in an SoC device.
All right, great, thanks. And actually, this one is also related to that slide. So there is the cryptographically secure pseudo-random number generator. Is that right? So there can be a PRNG that can be used for cryptographic algorithms. Is that correct?
Yeah, that is correct. Actually, these cryptographically secure PRNGs are standardized as part of the NIST SP800-90 series. And the important thing to note is that this cryptographically secure pseudo-random number generator is periodically reseeded with fresh entropy, basically meaning, and this is one of the, not the only one, but one of the fundamental requirements of a cryptographically secure pseudo-random number generator.
All right, thanks for the clarification. You mentioned that there are online health tests and offline health tests, and at least the offline health tests require a massive amount of random bits. So how can the online health checks work? Does those need to process every bit, and does it require a very large buffer or very large amount of random bits to be accurate?
Yeah, so that's obviously a very important topic, and I'll start briefly on the offline health test. And like I said, Walter, they do require a lot of data, and that's why we are talking literally about gigabytes of data, and that's why doing that kind of a testing online would be practically impossible. And that's why the online health tests are computationally much more lighter. And for the adaptive proportion test, we require maybe a kilobit of data for that to be run. And the repetition count is even, I would say, lighter in terms of resource requirements. So the online health test is kind of like they have been defined purposefully by NIST to be, I would say, implementable and executable on runtime, just to test for the quality of the entropy source output on the fly.
All right, thank you. What if one would combine two true random number generators? Would it be more secure than just one? And what if the other fails and starts outputting, for example, all zeros or all ones?
Yeah, so that's actually a scheme that is being implemented in certain places where basically the two random number generators might be based on different physical phenomena and would act as kind of like a backup to each other. However, a well-designed two random number generator on its own achieves a required entropy level and randomness level on its own. So I would view this type of a setup as a sort of a more traditional backup scheme. And if in case the other one fails, then obviously the system will still be able to produce reliable random numbers, provided that obviously that they are connected to the same entropy pool or pseudo-random number generator.
All right, thank you. Let's continue with the topic of different true random number generators. So is there any way to differentiate between output of an TRNG, for example, of a quantum random number generator?
Differentiate the output of a QRNG and a TRNG, is that the question?
Yeah, that is the question.
Okay, so I'm not sure if I got it correctly, but a QRNG, if properly designed, is also a true random number generator. So differentiating the output of a QRNG from, say, a quote traditional unquote digital electronics based TRNG should not be possible. They should both produce randomness, obviously not identical randomness, but randomness of a sufficient quality.
Yeah, so can we expand that question to, for example, pseudo random number generator? Can that be differentiated in any way of a TRNG?
Yeah, so now we get to the mathematics of pseudo random number generators, and in principle and sometimes also in practice, you can identify that somebody is using a pseudo random number generator because of the mathematical properties of the output that it produces. And to simplify a little bit, the pseudo random number generator has a certain cycle, and this cycle can be very, very long, but it still has a cycle. And this cycle, when it's achieves its end, then pseudo random number generator will start outputting the same sequence all over again. So that's kind of like the reason why a pseudo random number generator has to be reseeded or sort of resetted every now and then at periodic standard defined intervals to basically have a different initial condition, and then it starts outputting a different sequence. But basically I would say if you just take a very short sample of the output of a pseudo-random number generator and a true random number generator, say just a couple of integers, for example, then it might not be practically possible to differentiate them. But here we are talking about the mathematical qualities, and they are very important for cryptography.
All right, great, thanks. And unfortunately, we are running out of time here and cannot answer all of your great questions at the Q&A box. And if your question was left without an answer, please don't hesitate to contact us, and we will go through all of your questions that you send us. And you can see the contact information at the bottom of this slide. And to remind you, this webinar was recorded, and this can be found from our webpage in a video or audio format, and all the other four webinars can also be found there too. And for our next webinar, which is going to air in early summer, so stay tuned for the exact date and the interesting cryptographic topic for that one. And thank you all for tuning in and attending our webinars, and see you during spring. Bye-bye.